Hello, everyone. As usual, please write your name on the chat area and we'll get started shortly. We're going to continue where we left off. We were doing example 5 and we only did part A, so we're going to do the other couple of parts there. And I'll remind you where we were in just a moment, okay? So we are doing vectors, and specifically how to find vectors of an arbitrary magnitude pointing in the same direction of a given one. So let's go back to the page to remind ourselves what we were doing. So this is a problem we last did yesterday. So we had these 2 points, the point 1, -2, and 6, 10. So 1, 0. And we first wanted to find out what is the position vector corresponding to PQ, and then a unit vector parallel to PQ. So we did heads minus tail to find out the position vector. So that position vector has these coordinates, 5, 12. And then the magnitude of that is 13. And then to find out a unit vector with the same direction, pointing in the same direction, all we need to do is divide this guy or multiply it by 1 over its magnitude. If we multiply by 1 over its magnitude, now the new magnitude of this vector is actually 1. And if you want 2 of them, you can always do the one that points in the opposite direction, right? So one pointing this way, the other pointing the other way, right? Here or there. And that's how we find these two. So we'll now continue with part B. Part B now asks for 2 vectors of length 2. 2 vectors of length 2 parallel to PQ. Okay. And what we want to do is we want to see, it's actually very easy, especially if you already have the ones that are unit. See, because we already know these 2 are unit. So all we need to do to want any size, I mean, it doesn't have to be length 2, it could be length 10, it could be length 27. All you need to do is multiply these ones that are unit by the magnitude you want, right? So for example, here, what we need to do is we should multiply, so answer, multiply by the scalar 2, the unit vector. Unit vectors in the direction, the unit vectors parallel to PQ. So here the answer is simple. So in one of them, we take 2 and we multiply 2 by this guy that we had calculated last time. So the answer will be 10 13ths, 24 13ths. And that's one, and the other is this one, which is just the negative of the first one, right? You don't need to recalculate everything. You can simply do the negative of the original one, and that would give you the other one that you want. All right? So that's the answer. Let's, if you really, really want to check, you can do it, right? So let's get the magnitude of this one. Let's be very, let's say that we don't believe the answer. We want to check that what is this for sure. So the magnitude would be this number squared plus this number squared. And this is 100 over 169. And then 24 is, I believe, 526 over 169. And when you add these two, you get 626 over 169. And believe it or not, this is The number of top is 4 times 169. So this is 2. So it works, and it should work because we already know that we already knew that this one was a unit vector. So you multiply by 2, you of course get now a vector of magnitude 2, right? We could have done it instead of 2. You can pick any other number and it will work the same way. Okay, part C. For part C is says express the vector PQ as the product of its magnitude and a unit vector. Express PQ as a product of its magnitude and a unit vector. And that's also easy because we already know the unit vector that points in the direction of PQ. So PQ, let's go back, PQ is 512. And we already know that the magnitude of this guy is 13. So all you need to take is the 13 out of 512. So here it is. We know that PQ is 512. And we already also know that the magnitude of PQ is 13. So all we need to do here is write then as 13 times 5 over 13, 12 over 13. And this is the magnitude. And this is a unit vector. Unit vector in the direction of PQ. Is that clear? All right. One other thing that we didn't do last time, and that is, it's out of the way. We didn't talk about the couple of vectors that have names. Okay, so I just wanted to let you know about that because we're going to be using it as well today. So 2 special vectors in the plane. So in the plane, there are 2 vectors that are important. This one, the one that has, it's a position vector, the position vector 1, 0. And this one, the position vector 0, 1. And because these appear a lot of the times, and you can use these to write all other ones, we call this one I, and we call this one J. So I goes on the x-axis, J goes on the y-axis, right? You can think of it that way. And the reason these are important is because now you can write other vectors with combinations of I and J. So every vector can be written as a linear combination of I and J. In the book, remember, these don't have the arrows on top. In the book, I and J show as bold, right? But I can't be drawing bold characters when we are, you know, writing, handwriting, or on the blackboard. It will be difficult. So instead, we put the arrows. So for example, if we do the one we were doing before, so this vector PQ is 512. But 512 is the same as 5, 0 plus 0, 12, right? And that's the same as 5 times 1, 0 plus 12 times 0, 1, right? And these are I and J. So we can write it as 5I plus 12J. So in general, you don't need to do all this work. You can simply think that We can write a vector in this form, in vector form, or you can write it in ij form by just remembering that the I is the first coordinate and the j is the second coordinate. Okay, so 5i plus 12j. Is that clear? So it's just like a different way of writing vectors, an additional way in which we can write vectors. All right, so good. So now we're gonna move on to the next section, section 13.12, 13.2, I mean. And we're gonna now learn about vectors in 3 dimensions. So the vectors we had been studying before were in 2 dimensions. This, by the way, is how we, so 2-dimensional space, we call it R2. This R is the real numbers, so it's like the real numbers cross themselves, the Cartesian product of the real numbers with the real numbers, right? X coordinate, Y coordinate. Now for 3-dimensional space, we have now three coordinates, right? We're gonna have the X coordinate, the Y coordinate, and the Z coordinate. So I'll show you some pictures in a moment, but first, let me show you visually, right? So imagine that this pen that I'm holding, the purple pen, is the X coordinate, right? So we have the X coordinate. We have then the Y coordinate. It's perpendicular like this, X, Y. And then we're gonna have another one, the Z coordinate, which will be perpendicular to the 3 of them, right? X, Y, and Z, like this. And so I'll show you a better picture and also a way to know in which order they should go. So right now we have X, Y, and Z. So let's take a look at the book, and it will explain something called the right-hand rule. So the right-hand rule, maybe I'll try to, let's see, that's gonna be a problem here because I think you see my reflection in the screen, but let's see if we try to figure it out. So the way you use it, so right now on the screen, so, right, okay, so this is my right hand, and I'm not sure if you're looking at the exact same thing, but you're supposed to use this is one direction, this is gonna be the X, then you flex your hand, and that's the Y direction, and then your thumb points in the Z direction, right? And then that works for wherever you have your hand. So if your hand is over here, and this is the X direction, then you go like this, that's the Y direction, and then that's the Z direction where my thumb is pointing. So X, Y, and Z. Those are the 3 ones, all right? Let me show you from the page in the book. Maybe it will be clearer because I'm not quite sure if you see me or my reflection. So right here is where you can see. So we have three axes, right? The X-axis, the Y-axis, and the Z-axis. And just like you see in this picture, you go, so right there, and let's see if I can, when I make it so it looks the same, I actually can't. So that, see, because you're seeing my reflection, so it doesn't, it sort of works if you imagine it that you're looking at it from my perspective. So from my perspective right now, that's the X, then the Y. So when I flex like this, that's the Y in that direction, and then my thumb points in the Z direction, right? So we use the right hand rule. If you do it with your left hand, it doesn't work, right? Then you're gonna get the opposite one. You're gonna go down, right? If I do it with my left hand, it's X, Y, and then Z would point in the down direction. So you wanna use your right hand rule. And then we locate points in this 3-dimensional coordinate system in the same way as we did it with the 2 dimensions. So for 2 dimensions, the only thing you had to do was to follow along on the X coordinate, then the Y coordinate, and then this time we have an additional one, the C coordinate, right? So I'll show you some examples of what I mean here. Let's take a look at the next page. Okay, so here's a little example. And well, this diagram is actually how you figure out where to plot a point in three-dimensional space. So what you want to do is you want to, so if you have the point with coordinates A, comma B, comma C, right? You want to start from the origin, and then you're going to move A units. If the number A is positive, you're going A units in the positive direction. So you go from here to here, right? Then once you move X units, A units in the positive direction, then you go B units in the Y direction. So from here you continue over here. And then finally you go C units in the Z direction. And that's how you can locate the point A, comma B, comma C, right? So now points have three coordinates to them, okay? Three coordinates. So here's an example of how we could draw the point 3, 4, 5, or the point -2, -3, -5, right? So let me show it to you on the paper, and then we'll try. I'll show you a different way as well. So this is example 1, and we want to plot the point, plot 3, 4, 5. All right. So first of all, first thing you need are your axes, right? And your axis should look like this. Should look like the C is always up and down. So this is the C. The X like this, and the Y like this. This is X, Y, and Z. And if you want, I put like dotted ones here to figure out the negative parts, right? So these are like, remember, they're like three perpendicular lines, right? This is not the best picture here. Not, that's better. Okay, so now we want to plot the point 3, 4, 5. So you go on the x-axis 3 units. So 1, 2, 3. You go in the y-axis now 4 units. So 1, 2, 3, 4. And right where these two cross in that plane, that's where we are so far. And then we need to go 5 units high. 1, 2, 3, 4, 5. That's the C coordinate. So you go right here, 5 units high. 1, 2, 3, 4, 5. And this is our point. 3, 4, 5. Is that clear? How you do it? So you go 3 units in this direction. 3 units in this direction, 4 here, and then 5 here, right? And then the resulting point, right, would be this one over here, as the one that has the coordinates 3, 4, 5. So,
Professor?
Yes.
I have a question. So do you use the right hand rule to know which way is positive and negative? Or how do you figure that out? Which way is the positive x?
Well, it depends on, see, that's the thing, right? In three-dimensional space, see, this is the hard thing. We make a diagram, and usually we try to pick the first octant. That's the part where everything is positive towards us, right? So right now, the part that is towards us is the part where everything is positive, right? But maybe you don't want it. Maybe you want it to see from the back, right? So the only important thing to know is which one is which. So let me rotate this picture a little bit and try to show you in a different way. So imagine for a moment that I rotate this thing around, and that for me now, this is the X, and maybe this is the Y, the positive ones. So these are the negative ones. And this is the Z. You see what I did? I sort of rotated my picture to the right. Yes? And if I try to do that picture here, well, I should do it in the same way. So I go 3 units in the positive direction, 1, 2, 3. 4 units in the positive direction for Y. And then 5 units up. 1, 2, 3, 4, 5. So that's the point 3, 4, 5. Right? Does it look the same in these pictures? Well, no, because I sort of rotated the axis here, right? I put them in a different way. Now, the important thing, and that's where you use the right-hand rule, is in how to label them. See, right now I went from, it's hard for me to show my hand, but imagine that this is my fingers are going this way, and I'm going from X to Y. So I'm going from X to Y, and then my thumb is pointing in the direction of Z, right? So my hand right now would look like, maybe I try to draw my hand here. So it will look like my thumb pointing up and like this, right? So I'm going from the X to the Y, and then my thumb is pointing up. And that's how I know where the Z should be going. Let me show it to you in a different way. So I have that point over here. So I drew an arrow so that you can appreciate where it is, right? And here in Mathematica, I can rotate my picture around. Yes, and you can tell. See, this is more or less the way I have it right now corresponds to the last one that I show you. So there's 3 units in this direction. There's 4 units in this direction. And then there's 5 units tall. And that's my point. My point is right here at the end of that arrow. That's the point with coordinates 3, 4, 5. But if I rotate this thing around, if I put it how I drew it the first time, it kind of looks like this. Kind of looks like this, where I have 3 units in this direction, 4 units. Actually, it's still a little crooked, like more like this right there. 3 units in this direction, 4 units in this direction, and then 5 units up. And this is the point right here at the top. Does that help? Right? It's difficult. Yeah. I understand, because it's difficult because we can't put on paper. Paper is a 2-dimensional medium, right? We can only draw things that are 2-dimensional. So it's the best way to appreciate things in 3-dimensional space would be to do them in 3-dimensional space, right? So if we could do a solid model of where the points are, that would be even better, right? But it's hard for me to convey that, right? At least right here with this Mathematica thing where I can rotate, I think it's better. So what I was trying to tell you, Michael, is that maybe I can also put it, like this, right? If I put it up, this is the same picture, but now I've totally messed up my axis, right? So now my axes are sort of pointing the other way around. Now we're looking at it from the bottom, right? And the important thing here to know is in which is the positive direction of each one of these. So right now we have, this is the X. This is the X over here. And the Y is this one, right? And then to go from the X to the Y, we follow the right-hand rules, and then the Z is this one over here. Okay, let's move it along and talk about some simple objects in 3-dimensional space. We're going to be talking about planes, really simple planes, actually, planes that are parallel to the axis. So let's go back to the book. And I'll show you some examples of simple planes. And so right here at the bottom, you can see some examples of simple planes. And these are planes that are parallel to the axis, to both axes. So this first example over here is an example of what kind of plane you get when you let x be constant. So for example, this one that you see here, the one in the forward of the picture, is the plane with equation x equals 2, because every point in this plane has x coordinate 2, and the y and the z coordinate can be whatever you want. So the y and the z roam freely, and that's how you get this plane, right? I mean, we only see a little bit of it right now, but it should extend in all positive directions. So that plane, the plane that cuts in this, like this direction, is the plane x equals 2. The one you see in the background, that's the plane x equals 0. That's the plane where you have the y and the z axis. So the y and the z can be arbitrary, but the x is always 0. Then in the picture in the middle, you see what happens when now the y is fixed. You have the plane y equals 0. Now it's kind of like a vertical plane, but rotated 90 degrees. A vertical plane like this, rotated 90 degrees. And also you have an example of y equals 4. So now the y coordinate is 4, and the x and the z move freely. So the x can be anything here, and the height can also be arbitrary. And then in the last one, you have examples of applying z, where z is constant. So the height is now constant. You can either be a height of 3, is the one on the top, and a height of 0, the height on the bottom. And now the x and the y are the ones that roam freely. They can be whatever type of numbers you want. Okay, so we want to talk about a few other things. To begin with, we want to talk about the distance. So what is the distance of 2 points in 3-dimensional space? How to find the distance of 2 points in 3-dimensional space? So let me go back to the paper. We're going to need to set the next page here. So before we go back, let me move to the next page, and then we'll show the paper. Okay. So here's the situation that we want to explore. So on 3-dimensional space, for x, y, and z, we have 2 points. The point P and the point Q. And say that the point P has coordinates x1, y1, z1, and the point Q has coordinates x2, y2, z2. All right? And what we want to find out is the distance. So that's the question we want to explore. What is the distance? What is the distance from P to Q? Or what is the length of the segment PQ? Okay, so here's how we're going to do it. So let's say that maybe this one has, so here are the parameters for this one. So this is x1, this is y1, and right here, from here to here, that's z1. And then for Q, maybe we go, maybe Q is like this, where this is x2, and here to here is y2, and this height is z2. Okay, so how can we figure out the length between those two? And it may seem like a difficult thing to do, but it's actually not that hard. So what you need to realize first is that we can do the same trick we did for vectors. So we can move one of these guys to the origin, right? So if we subtract y1, x1, y1, c1, it's like moving it to the origin, right? So we can first do, you know, like we were doing for vectors, subtract the head from the tail, so that we move one of them to the origin. So in that way, my picture will be a little simpler. Let me redo it here. So if one of the points is the origin, and the other point is now the one that has coordinates x2 minus x1, y2 minus y1, and c2 minus c1. So let me call this q prime, because it's not q anymore. It's just, so this is now p prime, and it's now 0, 0, 0. Right? So we subtracted x1, y1, c1, and that has the effect of moving this point to the origin. And that's good, because it allows us now to do the calculations in an easier way. You'll see in a moment. So what I want to know is, what is this length? The purple length from P prime to Q prime. And we're gonna do it in 2 steps. First, we're gonna find out this dotted purple line. What is the length of that one? And to do that one, what we're going to do it is by using this right triangle, right? This is a right triangle, this one over here. Let me shade it. That's a right triangle, right? It's a right triangle on the XY plane. So this is X and this is Y. And so I can use the Pythagorean theorem to find out the dotted line, right? So let me call that W, the length of the dotted line. Yes? So first, what is this length from here to here? Well, that's simply the x coordinate of Q prime. So that's x2 minus x1. Now from here to here is the y coordinate of Q prime. So that's y2 minus y1. So the length of W, I can get it using the Pythagorean theorem. So I know that W squared is x2 minus x1 squared plus y2 minus y1 squared, right? And I'm gonna leave it like that. I'm not gonna take the square root, because I wanna keep going. Now, because the one I really want is this, the purple one, right? The purple one is the distance we are looking for. Let me call that one D, for distance, because that's the one we want. And then all I need is to know this height. Well, that height is the height, the z coordinate of Q prime. So that's z2 minus c1. And this triangle over here, let me now shade it with green. It's also a right triangle. The right angle is right here. Right? It's a right triangle that is vertical, right? It's like a vertical right triangle. Yes, but we can use the Pythagorean theorem on that right triangle as well. This time the hypotenuse is D. So D squared is W squared plus the height squared. And the height is Z2 minus C1. Now if you combine these two, what you get is that D squared is, instead of W, I now write all of these, is x2 minus x1 squared plus y2 minus y1 squared plus c2 minus c1 squared. And that is now my formula for the distance between 2 points. Here it is you take the difference of the x coordinate and you square them. You take the difference of the y coordinates and you square them. You take the difference of the z coordinates and you square them. You add them up. You take that big square root of everything. And that is the distance from the point P to the point Q. All right? Is that clear? See, that's what's our explanation. So it looks a lot like the distance when the points were in the plane. When the points were in the plane, it was like this, right? It was just cover this part, This was the formula for the distance for 2 points. X2 minus x1 squared plus y2 minus y1 squared, square root of that. Well, it's the same formula if you think about it. You just gotta add this extra term, the part that has to do with the z coordinate that we didn't have before, the contribution of the z. All right. So there's one additional thing here, and this is the midpoint and the sphere, the formula for a sphere. So let me go back to the book to show those. Okay, so this is like the diagram of the one we just did, a slightly different one, but the conclusion is the same. This is the distance between 2 points that we just deduced, how to figure them out. And now I wanted to tell you about the midpoint. And the midpoint is actually very easy. So here's a picture. So if you want to find the midpoint of 2 points, you do it the same way as you do the midpoint of 2 points in the plane. All you need to do is find out where is the middle of the x-coordinate. And the middle x-coordinate is the average of the x-coordinates. It's x1 plus x2 over 2. What's the middle of the y-coordinate? y1 plus y2 over 2. And then what's the middle of the z-coordinate? z1 plus z2 over 2. So you put the average of those 3 coordinates together, and that will be the coordinates of the midpoint. Okay, so that's an easy one to do. Can be explained using similar triangles, but I'm not going to do it. It's sort of, I think, straightforward to understand. And using that, now we can try to come up with the equation of a sphere. So the equation of a sphere centered at the point A, comma B, comma C with radius R. So that's what we want to do. What is the equation of a sphere centered at A, comma B, comma C with radius R? Okay, and we're going to deduce it using what we just learned. So what is it that we just learned? We learned how to get the distance. Okay, so what is the definition of a sphere? The definition of a sphere are, so how do you create a sphere? Well, it's kind of like how you create a circle, right? How do you do a circle? You take a point, you take your compass, and you take the distance, you keep the distance the same, and you go around. Well, the same with a sphere, only you go around in 3-dimensional space, right? When you go around in 3-dimensional space, you create a sphere, right? So the sphere are the points that are all at distance r from A, B, C. So a point x, comma y, comma c is on the sphere if and only if the distance from XYZ to ABC is R, right? And we already figured out how to get the distance. How do we get the distance? Well, we do this minus that. So X minus A squared plus Y minus B squared plus C minus C squared. Square root of that equals R. So that tells you what is the equation of a sphere. See, we don't like the square root too much. So instead of writing it like this, we write it as follows. So the equation of a sphere is x minus a squared plus y minus b squared plus c minus c squared equals radius squared. That's what it is. And if you remember the equation of a circle, the equation of a circle is essentially like this, but there's no c. That's the equation of a circle, right? If you remember from high school, right, when you did the equation of a circle, it was exactly this. X minus a squared plus y minus b squared equals the radius squared. So this is the same thing, only we now have an additional variable z, okay? So that's the sphere. And we'll, let's maybe do an example here. So let's do example 3. Example 3 says, consider the points P, 1, -2, 5, and Q, 3, 4, -6. Find an equation of the sphere with PQ as diameter. So the PQ is the diameter, and now we have to find the equation of the sphere, right? So what do we need to find the equation of a sphere? We need two things. We need the center of the sphere and the radius of the sphere. Okay, those are the two things we need. So how do we find the center first? If it was a circle, how would you do it? If you know the diameter of a circle, how do you find the center of the circle? Okay, divided by 2. The divided by 2 gives you the radius, right? If you know the diameter, how to get the radius. But I want to find the coordinates of the center. So how do we find the coordinates of the center?
Isn't it A and B?
A and B?
Yeah.
Yes, so we want to find out A, B, and C. And we have these 2 points, right? 1, -2, 5, and 3, 4, -6. So in general, if you have the diameter, how do you find the center? Right, maybe.
Would you subtract the diameter from a point?
Subtract the diameter from a point. Well, a point has 3 coordinates, right? Let's see if I do have a sphere over here. Yeah, so say I have a sphere like this, right? And I have the diameter. So the diameter is, well, I mean, 2 points that are opposites to each other, right? How do I find the center of the sphere? And it has to do with something we just learned, right? Isn't it the midpoint? The point right in the middle? So if let me do a picture here of an arbitrary sphere. So if I draw a sphere here, somewhere, there's my sphere, and I have 2 points that are the diameter of the sphere. So maybe this one and that one. So here's the center of the sphere, and I have 2 points, right? P and Q. I mean, these are not precisely the coordinates of P and Q in our picture, in our problem. I just want to illustrate how you find the center. So if you have P and Q, and that's the diameter, how do you find the center is the midpoint, right? The midpoint of P and Q. Is that clear? So what is the center? The center is the midpoint of P and Q. And so what is the midpoint of P and Q? Let's call it M. Remember how to get the midpoint? We're supposed to do the average, right? We need to do the average of the X coordinate, the Y coordinate, and the Z coordinate. So the midpoint would be 1 plus 3 divided by 2, -2 plus 4 divided by 2, and 5 minus 6 divided by 2. So this is 2, 1, and -1/2. So that's the midpoint, right? And yes, so now that you have the midpoint, these are A, B, and C. So on the equation of a sphere, we needed A, B, and C, and now these are A, B, and C. Okay, and now how do we get the radius? And that's maybe the question some of you were answering before, right? How do we get the radius? Well, the radius is from here to here, or from here to here, right? So we can do many things now. We can get the distance from M to Q, or we can get the distance from M to P, or we can get the distance from P to Q and divide it by 2, which is why a few of you answered, Nancy, for example. So what is the radius? Several ways. Several ways to get it. R could be the distance from M to Q, distance from M to Q, or also the distance from M to P, or also half the distance from P to Q. And that's the one I'm gonna do. I'm gonna do half distance from P to Q because I have P and Q available, right? So I'm gonna do that. Half the distance from P to Q. And that's distance from P to Q is, here are my coordinates, so it would be 3 minus 1 squared, or minus negative 2 squared, and negative 6 minus negative 5 squared. Let's see what that is. 3 minus 1, that's 2, 2 squared. 4 plus 2, that's 6, 6 squared, and that's negative 11, so that's 11 squared. So this is 4, 36, and 121. So that's 40. 40 plus 121 is 161. I'm gonna leave it like that. Okay. So finally, what is my sphere? So the equation of my sphere, what the problem that we were working with is now we can go over here. X minus a squared plus y minus b squared plus c minus c squared equals r squared. So here's the equation of the sphere. Is x minus, what is the a? Right here, 2. Plus y minus, what is the b? 1. Plus c minus, what is the c? Negative a half, so it's plus, equals the radius square. So that's 1/2 root of 161 square. And that's it. That's the answer to my question. Now, we also have the opposite problem, which is, what if I give you this, and I ask you, what is this? What does this represent? And then you need to tell me, oh, that's easy. This is a sphere with radius, this number, 1/2 of root 61, and centered at the point with coordinates 2, 1, negative a half, right? So easy if you have it in this form, but not so easy if it's expanded. And that's what the next example is about. The question is, describe the set of points that satisfy the equation, and here it comes. It's x squared plus y squared plus c squared minus 2x plus 6y minus 8z equals -1, right? And that's what I was telling you. So how do I know it's going to be a sphere? I actually can tell. It's going to be a sphere whenever, or well, maybe a sphere, maybe nothing, when you have x squared, y squared, and c squared, right? If you have these and they're all multiplied by the same number, in this case 1, then it's a sphere. Now, how can I tell what kind of sphere it is? What I need to do is complete the squares, right? So that's the work we need to do. So complete the squares. So here's how we do it. X squared minus 2x, so the x's together, And then I'm going to add something here to complete the square. Then the y's are y squared plus 6y. And then I'm going to add something. And then the z's, this z squared minus 8c. And then I'm going to add something. And that's -1. And whatever I add here, I better add on the other side as well, right? Now you know, or you should know, how to complete the squares. So what should I add here? Well, the way to do it is you take this number, the x coefficient, you halve it. So the half of -2 is 1. And then you square it. So 1 is what goes here, right? Similarly here, you take 6, you halve it, that's 3. 3 squared is 9. And then last here, the 8, you halve it, that's 4, so you add 16. And then whatever I added on the left, I better add on the right as well. So this is plus 1, plus 9, plus 16. Is that clear? It's just completing the square. I'm not doing anything calculus related here. And then you just put these guys together. So this is x minus 1 squared plus y plus 3 squared plus c minus 4 squared equals, what is this? The ones go away, 16 plus 9, that's 25, which is 5 squared. All right, and now we recognize it, right? Now what is this? This is a sphere centered at 1, -3, 4, with radius 5. Okay, is that clear? How it works? Okay, fantastic. So in the last, what is it that we have, 8 minutes or so, what I want to now talk about is vectors. Vectors in 3-dimensional space. And fortunately, most of what we have done applies in the exact same way. So most of what we talked about last time works out in the same exact way. So here's a little bit of what I want to tell you about. So right here, if we go, I need the next page. So how do we look at vectors in 3-dimensional space? And the answer is in the same way. So vectors have direction and magnitude, right? And the only thing, the only new thing we have in 3-dimensional space is that before, the directions were all on a plane, right? The direction meant an arrow in the plane pointing somewhere. Now it's an arrow in 3-dimensional space, right? You get an arrow that can point wherever you want in 3-dimensional space. So if we have a vector like the one you see on the screen right now, that is vector RS. Let me draw on top of it. Maybe thicker one. Let's see. Yeah, this one, RS, right? If we want to make sense of that vector in 3-dimensional space, what we want to do is we want to move it to the origin and then figure out what are the coordinates of the head. And if the head has coordinates v1, v2, v3, then the position vector that corresponds to RS over here is the vector that we write as v1, v2, v3. So that's the same way, right? Exactly the same as we did it with 2-dimensional space. The same way we can do it with 3-dimensional space. And the same type of properties hold. So if we want to add 2 vectors, we can follow the triangle or the parallelogram rule. Right here on the left, we have a little example of what it means to add up 2 vectors, right? And it's the same picture. You don't even see any difference. So this is a picture of the triangle or the parallelogram rule, and you can see it illustrated right here. with adding these two vectors, the vector -2, well, whatever two vectors you want to add, you can do them following the parallelogram rule or the triangle rule. And right here on the right, you can see how you can do it if you have position vectors. If you have vectors u and v, then the way you can add them is if you simply add the corresponding coordinates, the corresponding components. If you add the x component, the y component, and the z components of u and v, that's how you get the vector u plus v. If you subtract the x, y, and z components of the vector v from the vector u, you get u minus v. And if you, a scalar multiplication means you multiply each one of the components by the constant c. All right? So to finish for today, let's take a look at this example 5. So we have now these three vectors in, these two vectors, sorry, in 3 space. The vectors 2, -4, 1, and that's u, and the vector v, which is 3, 0, -1. And we want to find out half of u, -2v, and u plus 2v. Let's do it. So here's our vectors. And the first one is, how do we do half of u? And that's easy, right? You just do half of this. And we learned that all we need to do is multiply this each component by 1/2. So this will be 2 times 1/2, that's 1. -4 times 1/2, that's -2. And 1 times 1/2, that's 1/2. That's it. Easy peasy. Part B is to do -2v, right? And that's -2 times the vector 3, 0, -1. -2 times 3, that's -6. -2 times 0, 0. And -2 times -1, that's +2. Boom, that's it, right? Last, part C. For that one, we have u plus 2v. So u is the vector 2, -4, 1. And v is the vector 3, 0, -1. I'm copying right now, and then I'm going to multiply by 2. That's 6, 0, -2. And now I'm going to add them. 2 plus 6, that's 8. -4 plus 0, that's -4. 1 and -2, that's -1. Right? Easy peasy. Okay, let's go back to the book because there are actually some pictures associated to this. So here's what we did for the first one. So we did 1/2 of u, and so that you see that it represents what we know it should be. So we had the vector u. Oops. I wanted to draw a vector from here to here, right? And what we're doing is we're halving it. We're doing half its length. So, and when you do half its length, what you get is that new little vector that goes from here to here, right? Half the length of the original one, okay? Next, on the graph on the right, oops. The graph on the right, you have the situation of doing -2v. So -2v, now we have this vector 3, 0, -1. And what we're doing is we are making it twice as big and pointing in the opposite direction, right? So you can see now how this red vector points in the opposite direction. And just to finish for the day, here's at the bottom how we add up u and 2v, right? So once that you have u, the vector with coordinates 2, -4, 1, with components 2, -4, 1, you are adding it to the vector 2b, which has coordinates 6, 0, -2. And when you do it, you obtain this one in the bottom, which is the one with coordinates 8, -4, -1. And we do it by following the parallelogram rule. You can see how the parallelogram is drawn in this picture right here. Okay? All right. So I'm going to stop right here. What we're going to do tomorrow is talk about now magnitude. So the same thing we did for two-dimensional vectors, we're going to do for three-dimensional vectors. So we're going to try to find out the magnitude of a vector, which is easy because we already know the distance formula. And then we're also going to learn how to find out, you know, a unit vector pointing in the same direction as a given vector. So the same thing we started today's class, but instead of working with two-dimensional space, we are going to add another dimension, and it will be three-dimensional space. All right? So I'm going to stop shortly. Are there any questions? All right. Very well. I'll see you guys tomorrow. Stay safe.